So in the last class, we have talked about this particular problem that we want to find a decision boundary. So we have started with linear discriminant function, and we want to find that particular line which will have maximum. For example, if I look at this particular example, so you can see that basically there are a lot of possibilities over there. And the question is that which one is the best? Okay, like we have seen that if we have a sample over here, and if we have picked this decision boundary, for the training set it's okay, but for the test set, okay, it's not okay because this sample is going to be misclassified. Okay, though according to the decision boundary it is okay, but if we think of the class level, it should be belong to this particular class. Okay, so now how can I do it? So if I take the other option, so this is, let's say this is option 1, and now we have this option 2. You can see that this is option 2. If I think from this point of that, how much distance are we maintaining with respect to the positive class and the negative class? Okay. If I look at this case 1, since we're talking about the distance, so this is the distance for the positive class is this much, the distance for the negative class is this much. Okay. But for option 2, if I look at the distance possibility, so you can see that this one is maintaining more distance in compared to case 1. So since we are talking about the distance, so we can think in another way around, like if I think that this is a very thin line, if I want to increase the width of this line, it's going to be a very thick line, right? Yes or no?
Yes.
But if I consider from the point of the other case, the case 1 actually, so if I consider the thickness, if I increase the thickness, you can see that the thickness of the possibility of case 1 is going to be very narrow. And we can see that if we can maintain maximum distance with respect to those two classes, what will happen? We believe that for new test samples like this one, they will be perfectly classified to the class they should belong to, right?
Yeah.
For example, in case of case 1, this sample was assigned to class 1, but if you take the decision boundary for that we are found in case 2, we found that it can be perfectly assigned to case for the class 2. Okay, so that means we have to maximize the margin. And the decision boundary we are looking at, since it is linear, that's why the classifier we are going to build is known as linear support vector machine. And why we have support vector term here? Because the samples, remember, these samples, we basically defines the margin of the decision boundary. That's why these are known as the support vector. I mean, these are sample points at the same time, since they are defining the margin. So that's why they are known as support vector, and the classifier is known as support vector machine. And the important thing is that the support vectors are the ones which are defining the margin. And later on, we'll see this margin, okay, it will be only dependent on the support vectors. And also to determine the value of W, you have to find the value of W. They are also dependent on the value of these support vector samples. Is this clear up to this?
Yes.
Okay, now how do we mathematically define the margin? Okay. So, but we know the decision equation of the decision boundary or the discriminant function. Let's say it was like W transpose X plus bias, that B should be equal to 0. That is actually what we have already have over here. For the time being, I won't write this transpose because I will think that it automatically means that we are doing this dot product over there. Okay. Now we know that if we have this sample over here, then the point from this line to that sample is somehow it's going to give us a representation of the distance. But purely from the point of the discriminant function response, let's say the function response is going to be W transpose X plus B is going to be equal to +1 for the positive sample. If I write for the positive sample, the response is going to be +1. For the negative sample, if I look at the negative sample over here, since the distance is equal on both sides, here we will see that the distance, the discriminant function value is going to be -1. That means if I take the difference between these 2 points, don't you think that I will get this margin?
Yes.
The discriminant function response +1 -1. Does it give you the distance?
Give you 0.
I mean, that's for the decision boundary, but I'm saying let's for the positive sample. This one does not give you a distance. It gives you a value proportional to the distance. Now we know already that from a point to the decision boundary, the distance, let's say if I represent like this, so let's say for the positive sample, if I want to compute the distance r, or let's write over here this value r, this arrow over here. So we know this distance is found by the response of that particular sample divided by the magnitude of w. So if I want to compute the response of the discriminant function, what is the response? What's the response? For the positive sample, what's the response of your function?
Positive one?
Plus one, right? Exactly. And then we can see that the relation between the function response, if I write like this is the function, discriminant function, if I write like this. This is the discriminant function. And here r means the distance. So what is the relation between the distance and the discriminant function? You simply have to divide it by the magnitude of w, right? Yes or no?
Yes.
Okay. That means for the positive sample, the distance is +1 divided by the magnitude of w. So if I say what is the distance? So if I write it, this is r plus means the distance for the positive sample. What is the distance for the negative sample?
-1 by magnitude of
w, right? So that means let's say this is equation 1, this is equation 2. So if I want to compute this whole distance from the positive sample, if I draw over here, these are the same values. So this distance as a whole should be equation 1 minus 2, right? Yes or no?
Yes.
And if I do 1 minus 2, what do we have? 1 by magnitude of w minus -1 magnitude of w. This becomes 2 divided by magnitude of w, right?
Yes.
Okay. So if this is the case, so that's why we see over here that we have defined the margin, okay, which becomes 2 divided by the magnitude of w. Is this clear?
Yes.
But we have one question over here. For the positive sample, that means the sample which is going to be supplemented, remember, we can also have some other samples over here for the positive class. For the negative class, you can also have some samples of the negative class over there. But exactly for the support vectors, can we ensure that the function response is going to be equal to +1? Yes or no? We cannot. That means since the value of the coefficient w and the bias value can be anything. So basically, if I simply consider like this, if I compute w transpose x, or let's just remove the transpose of the whole thing. For the positive sample plus b, this for the choice of w and the choice of b, this should be any value w, any value v, right? Yes or no?
Yes.
Fine. But I said that for the positive sample, this has to be equal to 1. So do you have equal to 1 over there? You don't have, right?
You don't have.
But we can do it very simply. That if I bring this v on the left hand side, that means we have w divided by v, simply but w is a vector. But still you can normalize it by v plus b divided by v is going to be equal to +1, right? That means you ended up with a different set of w and a different set of bias, but still basically this thing we can say that we can write like that, right?
Yes.
So, but since this w and w prime are different, but do they represent the same line?
Yes.
Yes. So that means it doesn't matter what is the value of w and b, we can always assume that, or we can think in this way, that from the decision boundary to the support vector for the positive class, the response is going to be +1, and for the negative class, the response is going to be -1. Understood? So that's why always you will see that you will find that the function, this is a function, margin, is going to be equal to what? 2 divided by magnitude of w. Okay? So we have seen the proper definition. So now what we are looking at, that means for different choices of w, because you have a lot of, as we have seen in the previous slide, we have a lot of lines, right? We have a lot of lines. Where do we go? Anyway, we have a lot of lines, right?
Yes.
We have a lot of lines. So each line is represented by a particular setting. This will have its own w, this will have its own w. But among all these possibilities, which one you will pick? You pick the one with the maximum margin, right?
Yes.
Okay, so since we're doing it, so that means what we are looking at, I want to maximize Okay, maximize the function m, and this function will take an input as w. And then if you say argument max, because I'm not interested in the maximum value, I'm interested in the value of w, what will it give you? It will give you the line which will maximize the margin. Is it understood?
Yes.
Okay. But we have a problem. What is the problem? Not only do you have to maximize the margins, if I write like this, you have to maximize m, that is 2 divided by magnitude of w. This is what m is. But you know that if I draw the figure that we have seen earlier, let's say the black one is the decision boundary. So this is sample from the positive class, and let's say these two are the samples from the negative class. Okay. But remember, do we only have sample vectors, or do we have other samples too?
We have other samples.
We have other samples too. Let's say this is a negative sample. I just draw it process of it. Okay. The thing is that we know that for the positive sample vector, it's going to be +1, the negative sample vector -1. For other samples from the positive class, don't you think the response is going to be even greater than 1?
Yes.
And for the negative classes, up to this one is -1. And if you look for other samples, the value will be less than -1, right?
Yes.
Fine. Now you can see that since the class level is represented by +1 and -1, so if I multiply this one with y, don't you think the condition will simply fit?
Yes.
Okay. How about for class 1? Basically, if I multiply with y, and here y is 1, basically the condition will remain the same, because y is only +1. Multiplying with 1 basically is the same thing, right?
Yes.
That means what we have done is, if we simply multiply the value of the function response with yi, that is the class level, you see that for both class 1 and class 2, the condition has become greater than equal to 1. So that means for basically what happens, if I multiply with y for the negative class, so the value of y for negative class is -1. So if you multiply any negative samples with -1, what will happen? All these samples basically they get reflected to the positive side. Yes or no?
Yes.
So this is actually what happens with the reflection. So that means if you multiply with y, if the value of y is +1 or -1, only then you can do like this. Remember, only whenever it is represented by +1 -1, then you can multiply it with y like that. Okay.
Okay.
Okay. But what was the problem? Okay, now we know that we have to maximize the margin. Okay, how about if I flip it upside down? Let's say instead of writing 2 divided by magnitude of w, I flip it, so the numerator and denominator like that. This will become basically magnitude of w divided by 2. So if I define another function j, I define the function j like that. So do you think you have to maximize j or you have to minimize j?
Minimize.
You have to minimize j, right? And the magnitude of w is basically found by square root of w transpose w divided by 2. So if I just remove this square root, whichever is going to be small, removing square root, still it will be small, right?
Yes.
So that's why, since we have done a lot of minimization, okay? So that's what we do. Maximizing the margin is equivalent to minimizing w transpose w divided by 2. Same thing, right?
Yes.
Okay. That means, let's say you have a function. Let's say I draw this function. This is now I represent with respect to w. This is j. Which point are you looking at? You want to minimize the value of j, and you're looking for this particular solution point, that is w star, correct?
Right.
But the problem is not that much simple. Why? Because you have seen that at the same time, this has to be true. What is that? That means all the samples, for the positive class or for the negative classes, okay, it doesn't matter. For all the samples, they have to maintain a distance so that the response can be greater than equal to 1, or for the negative classes will be less than equal to -1. That means your problem has been formulated as, I want to minimize this function. I have used theta, they have used theta here, but let's say we consider this is j, because since we have used this term very often, let's say j. So that means I have to minimize this function, the criteria function j, but at the same time I have to fulfill these conditions. The question is that, how many conditions do we have?
2,
No.
1.
Since we have n number of samples, this should be true for how many samples? For all samples. And let's say if I give you n number of samples, okay, we have n number of samples. Then how many conditions we have?
Any number.
N number of conditions. And how does it look like? Okay, let's say if I show you like this, if I draw you like let's say I will show you a figure. Okay, let me show you a figure. That's better. Can you see the screen?
Yes.
Okay. Now look at this particular example, this particular figure on the right hand side. So that means here what we are looking at this 2D space. I want to find the maximum of this function, and all the values are plotted over this XY space. So can you see my cursor? Yes or no?
Small, but we can see.
Yeah. So don't you think the function maximum is over here? The point I pointed my cursor. Yes or no?
Over where?
My cursor, look at the tip of my cursor. Don't you think that's the maximum of the function? Can you see it?
Sir, we can't see the cursor. Okay, now it's...
Okay. Can you see the cursor now?
Yes.
So don't you think the peak, the maximum of this function is going to be here? Yes or no? Right?
Yes, sir.
Okay. But that is what if you had simply fulfilled this particular condition. That is, I want to maximize the function, right? Yes or no?
Yes, sir.
Okay, what is the picture? Okay. But you can see that here we have another thing. That means you have to fulfill a particular condition. Okay. So let's say this condition is being represented by this red line. Can you see the red line?
Yes, sir.
Okay, fine. Now the thing is that if I look at the maximum of the function, is it on the red line?
No.
No. Then if I say I want to find the maximum of this function, at the same time it has to be on that red line. So where will it be? Don't you think it is going to be somewhere there?
Yes, sir.
Okay. So that means if I say I want to find the maximum of this function only, you want to find somewhere over here, right? But once we give a condition like this, we have given a condition like I have to fulfill one condition. That means you have to be on that line, right? Yes or no?
Yes.
In our case, how many conditions do we have?
Any number.
M number of lines. That means basically what it means that you have to find the maximum of, or since we are doing minimization, you want to find the minimum of the function. At the same time, you have to find what?
Maximum.
You have to find the minimum. At the same time, you have to be on those
On the
number of
right.
lines. Is this understood? Just a minute. I can go to full screen. Is the problem clear?
Yes.
So this is what happened actually. That means now we are facing a constraint optimization problem. Okay, that means we have a, that means I want to, that means as if we have a function. Let's say just simply if I think like this. Let's say the minimum of this function. Okay, if I draw like this, the minimum of this function is of course it is here. This is W for that particular. But it says that you have to find the minimum of this function. At the same time, it has to be on one of the lines. So where do you think the solution should be? Do you think it should be here?
Yes.
If I didn't give you this particular condition, then of course the solution would have been here, right?
Yes.
But I gave you one condition. What does it mean? The solution should incorporate and fulfill this particular condition. That means basically what we have, we now have a quadratic optimization problem, and not only is it quadratic, it's also a constrained quadratic optimization problem. Okay?
Okay.
Okay, now next what we have to do, since I want to find the solution, okay, since I have to find the solution, so what I will do, I will use this Lagrange multiplier. Okay, I have to use this Lagrange multiplier. So I believe you don't have this Lagrange multiplier, but still what I will do, we can convert this problem into its dual form, and you will see that in case of Lagrange multiplier, you only have to find the multiplier value that is alpha over here. Now you may ask me, what is the Lagrange multiplier, right? Yes or no?
Yes. Yes.
Okay. So what I will do now, I have to switch my screen. So this is the problem. Can I share my whole window? Entire screen. Okay. Okay, I think this is better. I believe you can see it, right?
Yes.
Okay. Can you see it now?
Yes.
Now the figure that I've shown you earlier, let's think from the point of, as the top view, okay? So where is the maximum point? Maximum of the function. The tip of my screen, right? Yes or no? Can you see my cursor?
Yes.
And if I have to find the maximum of the function at the same time, it has to be on this condition line. Then where is going to be the maximum?
Right there now.
Right there.
Yeah.
Yes. Now you can see here at this particular point, if I compute the gradient of the function, only the gradient, it will point in which direction? It will point towards the maximum direction, right? That means this small arrow is basically showing you the gradient of this function f. And if I compute the gradient of the condition, the red line is basically giving you the gradient of the condition. So do you think that they are perpendicular to each other?
Yes.
But are they equal?
Are they?
Are they equal?
No.
They are of equal? No, of course not, right? So you will see interestingly in case of this Lagrange multiplier, okay, let's move directly to my okay, I think what I will do, I will switch my screen, sorry again. You can see my screen, right?
Yes.
So what I mean is that since we have seen that means the gradient of this function f and the gradient of the condition, whatever condition is and this right hand, this is the condition g. Since we want to say they are perpendicular, parallel to each other, perpendicular to each other, but are they same? Can I write this symbol equal?
No.
No. But if I include a multiplier, let's say I include a multiplier alpha, then can I write it as an equal? Yes or no? We can, right? Let's say we have this vector, and then we have another vector in this direction. So this, let's say this is del f, let's say this is del g. So let's say if del f is half of del g, don't you think that the alpha value is going to be half?
Yes.
So that means since they are perpendicular to each other or they are parallel to each other, we simply have to include a multiplier value, and that multiplier value will basically make them equal. The question is that what is the multiplier value, right?
Yes.
That is what we keep for later. But if we bring them on the same side, don't you think your equation will become something like this?
Without knowing the value, but yes.
Yeah, without knowing the value, let's say we'll find the value later, but I just brought everything on the left hand side. So this has become something like that, right?
Yes.
So this equation is basically what we say that let's say if I took the equation at the very beginning, f minus alpha g equal to 0, this equation is known as the Lagrangian form, or the Lagrangian, you can say like that. Okay, so let's say we write like this. A is equal to this Lagrangian function. Okay, and if I take the derivative of A, don't you think the derivative of A will be the line that we just wrote below? Yes or no? Or if I can write this del L is going to be equal to 0, right? So that means this is same as the equation that we have in the middle. Yes or no?
Yes.
Okay. You'll see that later on that since I only have one condition, that's why I will have only one multiplier alpha. But if I have another condition, so basically you see the equation will come to something like minus lambda, or let's say GH equal to 0. So it will have lambda 1, lambda 2. So if I have n number of conditions, then basically in our case, how many Lagrange multipliers do you need?
Any number.
We have to have n number of Lagrange multipliers, right?
Yes.
So basically, I won't show you the details, mathematical details over here. With some simple manipulation, you'll see that the Lagrange multiplier, if we use them, we can convert it to its dual form or dual problem formulation, and we see that whatever we're trying to solve now, this has ended up finding a value of lambda I. Now, this is what your problem has converted to. And interestingly, you see that once we have done this manipulation, we have found that the value of this lambda I is going to be greater than or equal to 0. This will be true for all the samples. Is this understood?
Yes.
Okay, fine. Now the question is that if I look back to the problem, let's say whatever I have seen before, let's say here I have the positive sample, and let's say here I have the negative samples over here, and also of course you have some other samples in the negative. Interestingly, you find that which one are your support vectors here? These three are your support vectors. And for the support vectors, the lambda values is going to be greater than 0. And for the non-support vectors, so if I draw the non-support vectors, let's say this one, this one, this one, this one, that one, and that one, for the non-support vector, you find that the lambda value is going to be equal to 0. So that's why you find that the value of the Lagrange multiplier, alpha value are going to be greater than or equal to 0. Is this understood?
Okay, yes.
Okay. This is number one. Number two is that, as I'm going to explain much, the combination of the Lagrange multiplier. First of all, you have found the value of the lambda I is going to be greater than equal to 0. And if you take the summation of these Lagrange multipliers, alpha, if you just simply combine them with their class level, you find that they will add up to 0.
Okay.
Okay. So these are the two conditions that you will find over here. And you later on you'll also see that the value of W becomes a linear combination of all the samples. But as I've said, for the non-support, because this Xi means all samples, remember, it means all samples. But what is being multiplied here? The Lagrange multiplier is multiplied, right? And we know that the Lagrange multiplier alpha I is going to be greater than or equal to 0. For which samples is going to be 0?
The one is that.
The non-support vectors, right?
Yes.
And for the support vectors, lambda value is going to be greater than 0. This is for support vectors. So you can see that automatically this summation is that we only have to consider only what? Support vectors.
Yes.
Okay. And we can see that that means the value of W, it means that we can simply have to take a linear combination of the support vectors. That means, let's say if I have like this, if I draw it again, that means in order to find this value of W, I only have to take a linear combination of the support vectors only, and this can give us the value of W. So that means basically to find the value of W, is it dependent on the number of m number of samples, or let's say how many? Let's say let's say n number of support vectors. Can I say like this?
Yes.
N number of support vectors. So this is one benefit of using this HVM classifier. We can find the solution simply from the support vectors. Okay, and the main thing here is that you have to know the value of the Lagrange multiplier. This is very important, right?
Yes.
Because once we find it, we know which one is the support vector, which one is not the support vector, and W can be found from the value of the support vectors. Okay, you have found, maybe you have found the value of W, but did you find the value of the bias B?
No.
Okay, how can you find it? Very simple. We already know the value of W transpose for the positive class. This response was equal to what? Equal to 1. Now, already you know the value of X, you know the value of W. To find the value of B, this is equal to 1 minus W transpose X plus, right?
Yes.
How about for the negative sample? What will happen for the negative class? You can also sample support vector for the negative class. W transpose X minus plus B is equal to what? Minus 1. So from here, if I want to compute the bias B, this is equal to minus 1 minus W transpose X minus, right? Yes or no?
Yes.
So we know that for the positive class, this value of plus 1 is the value of Y for that class, and minus 1 is basically the value of the class level from the negative class. Yes or no? Right?
Yes.
So that's why you see that the value of the bias B, we can simply write with this particular equation, that means Y minus W transpose X. So that means you can do it for any value of X, right? This any value of X means with any value of support vectors. Yes,
Yes.
sir?
Yes.
So now you know the value of B and you know the value of W, and of course all of them, what we have done, we have already maximized the function M, right? We have already maximized it. Yes or no? This is your W star, this is your bias delta B star, right? That means whatever you are looking for. Now once you have done it, so once you want to go for testing, what do you have to do? You simply have to compute F equal to W transpose X plus B, right? Yes or no?
Yes.
That means all these value of W and B will come over here and you can find the value of F. Correct?
Correct.
Okay, but again I can see that the value of W, I have found that the value of W can be written like this. Yes or no?
Yes.
So they can see that here we have this part is basically what? This is your W transpose, right?
Yes.
And of course you have your B over here. Now once you see this particular representation of W, you can see that because of this W transpose, what we have? You have your X transpose over there. So if I particularly look at this particular point over here, that means basically what I'm doing, whenever I'm doing a test, we are doing a test with a sample X. What we have to do, we only have to consider the dot product. The dot product between X and the support vector. Yes or no? Let's see if I write like this. Yes or no?
Whenever
we are computing this X transpose X, we are basically computing the dot product between the unknown sample X and the support vectors. Yes or no? Let's say V dot, let's say, or write like this, let's say U dot V. If you want to compute the dot product and if they are normalized, what can we write? We can simply write U transpose V, right? Yes or no? Right? So if that's the case, so what are we computing here? We're computing X, I means this is the support vector, transpose the test sample X. So don't you think that basically we have simply computed the dot product or inner product? Yes or no? And this dot product, is it a linear operation or is it a non-linear operation?
linear.
Okay, so that's why what we are looking at, this is the solution for a linear HVM. Is this clear? Is it clear? So up to this, do you have any questions? Yes or no? Okay, I just want to exclude this part for the time being. Okay, I want to move to non-linear SVM. So these data sets, can they be linearly separated? Yes or no?
Yes, sir.
How about this data set?
No.
Because, and let's say what I do, if I look at this particular example here, can these be linearly separated? Yes or no? Of course, they're linearly separated, right? Because the feature space, previously, if the feature space was one dimension, okay, it's different feature space that is, let's say this is two-dimensional, right? Yes or no? Are you with me?
Yes, sir.
Okay. But how did I get this? How did I transform to this two-dimensional space? The value of z I've computed like this. The first element is going to be x. The second element is going to be x squared. So isn't it what we have seen earlier that we do this phi transform? Yes or no?
No.
Why no?
I don't know, sir. So it's the same?
Basically, what we have done, basically we have defined the transformation using this function phi, which is phi function. This phi function, what it does, it will transform the data from the previously the x was one-dimensional space. For example, let's say this value of x was equal to let's say 2. So if I move to this z space means the transformed space. Then the same sample, if I show over here, the same sample, though it's not exactly like that, or maybe if I look at this one, maybe this is the one. Or no, it's okay. This is 2. The same sample in the z space will be represented by which vector? Let's say x was equal to 2. In the z space, it will be what?
2 dimension.
2 dimension, but the values are going to be something like, if I draw like this, since I have this x square, and then anyway, it doesn't matter. So don't you think it's going to be 4, 2?
Yes.
And if I plot it in this z space, is it going to be one dimensional or is it going to be 2 dimensional?
2 dimension.
And if I do it for all the points, don't you think that all the points will be now in the 2-dimensional space?
Yes.
Fine. And you see that these samples in the 1D space, if you transfer to this new space, the samples will be plotted like this. Now, once you plot like this, if I can find this decision boundary, can I linearly separate them?
Yes.
But in the original 1D space, can I linearly separate them? Yes or no? I cannot, right? Because we'll have a misclassification here. And if I take the decision boundary right over here, we'll have misclassification. That means basically, if we can not linearly separate the data in the original feature space, what can we do? We can transform them into this higher dimensional space, and then we can try to find a linearly separable decision boundary. Is this clear?
Yes, sir.
Yeah.
Okay. Now the problem is that if I do it with the support vector machine, then this support vector machine in the Z space, is it linear?
No.
Yes, it's linear. We found a linear decision boundary.
Yeah, but it's not class. Okay. Okay.
It's a linear support vector machine, right? Yes or no?
Yes, sir.
However, if I look purely from the point of x, is it linear? Okay, let me make it easy for you. this line and the samples, once I move to the Z space, it has become an arc like that, right?
Yes.
And then once you have found this decision boundary, if I draw with the black line over here, this is the black line is the decision boundary. This black line has intersected your original line in which points? Here and there, right?
Yes.
If I were to look to those points purely from the X feature space, don't you think the points will be somewhere here and there?
Yes.
So in the Z space, you have a linear support vector machine. If I look from the point of the X space, is it linear or is it non-linear? It's non-linear, right?
Yes.
So do you see the interesting thing? You have mapped to a high-dimensional space. You found a linear SVM machine, but practically that is non-linear in the original feature space. So that's why we say that we have developed a non-linear support vector machine. Is this clear?
Okay. Yes.
Okay. So in this case, what do you have to do? First of all, you have to move from the X space to the Z space using this phi function, right? Yes or no? And then if I want to find this linear decision boundary, I have to find the value of W. The W value is going to be like something like alpha I, y I, that is going to be Z I, right? Since we are in the Z space, yes or no?
Yes.
And let's say we already also found the value of bias B. And if I look at my decision boundary, this particular decision boundary, the linear decision boundary, then your decision boundary will be something like W transpose X plus B equal to 0. Sorry, W transpose Z, because in the Z space, my mistake. And then, if I want to replace W with this side, right hand side, this is going to be summation of alpha I, y I, Z I transpose Z plus B equal to 0. Yes or no? Right?
Yes, sir.
Okay. Now, do we have a dot product between the support vector in the Z space and the test sample? Yes or no? Do you have a dot product over there? Yes, we have it, right? Is it linear? I'm asking the same question again and again. Is it linear? Yes, it's linear. How about I want to, from this equation, okay, I just want to save some space over here. How about if I want to look it from the X space, what should I do then? Instead of Z, how do you find the value of Z? Z will equal to phi of X, right? So now let's see. From here, I will just write the equation above. So what we have? Summation of alpha I, y I, then we have phi x I, then you take the transpose, and then you have phi of x. Isn't it what we have? Yes or no?
Yes.
That means instead of Z, I simply have written phi of x. Okay?
Okay.
So that means in order to perform this linear SVM in the high dimensional space, you have to transform from the X space to the Z space, and then you have to move back from the Z space to the X space, right?
Yes.
Yes or no? And then that is when basically what we have. You have the non-linear, you have a non-linear SVM in the X space, right? But it's expensive, don't you think?
Yes, it's expensive. It's too much work.
Yeah, you have to compute the phi function, compute Z, find the linear SVM in the Z space, and then move back to the X space. That means in the X space, it will be something like this. Now, if you consider from the point of X space, is it linear or is it non-linear?
Non-linear, sir.
Non-linear.
Non-linear. Why it is non-linear? Because the phi function, we have seen that phi function was equal to x square x, right? You see that the non-linear term is there, right? Then what should you do? Like I've shown over here. So we have a 2D example. This is the X space. This is the Z space. We have done this phi transformation. Now, once we have reached this 3D space, are they linearly separable? Yes, right? They can be linearly separated. But the problem is that it's very much expensive. That means since we have to look at this dot product, that means the dot product between Zi transpose Z, or to separate them, so this is Zi, this is Z of J. And we know that Zi transpose is same as phi of Xi transpose, and Z of J is equal to phi of Xj. That means basically what you have to do. You have to compute the dot product or the inner product, right? And to do this, you have to transform from Z and then compute the dot product in the Z space, and it's basically expensive. But what I will do now, we'll use the kernel trick. What the kernel trick does, basically you will compute the dot product in the X space, but it will give you the same value if you have done the dot product in the Z space. Do you understand what I have done over here? Is it understood?
So can you repeat it again?
Okay. That means, first of all, this is clear that I have to do the dot product in the Z space, right?
Yes.
Okay. But what I will do, I will not do the dot product in the Z space, but I want to have the same value. That means I want to have the same value as doing the dot product or inner product in Z space, but I want to do all the calculation. But this is very important. I want to do all calculation in X space. So if I do all calculation in the X space, but I get the equivalent in the Z space, don't you think that you just got relieved from the computation of phi of X? Yes or no?
Yes.
That means I don't have to calculate phi of X. I don't have to do it. But yet, what do I get? I get the value of doing the dot product here. The question is that how is that possible actually? It is very much possible like this one. What they have done, they have defined some kernels. The kernels have some certain criteria that we fulfill. Let's say, for example, here we have a polynomial kernel. A polynomial kernel of order of 2. So do you think that if I do this computation, can I do it in the X space? Remember, can I do it in the X space? Yes or no? I can do it, right? Because I can see that X transpose X is there, and then I add with 1, and then I take the square. The thing is that if I do the expansion, now mathematically, look at this one. If I do the expansion of this particular equation over here, that you started from there, you can do factorization and you ended up with factor of this multiplied by that. So basically what does it give? It gives you basically Z transpose Z. Can you see that? Z transpose Z?
Yes, sir.
So that means if I say Z, I'll just omit the subscript. Z is equal to phi of X. So don't you think the phi of X has been defined something like that? Yes or no? So purely from the point of Z, you can see that you have a vector, right? 1, 2, 3, 4, 5, 6. There are 6 elements in that vector. And if you want to do the dot product in Z, basically you just come to Z dot B, basically you have a linear SVM. But if you omit Z and if you look purely from the point of X, is it linear or is it non-linear? Is it linear or non-linear? It is non-linear, right? You have x1 square, you have x1 to x2, you have this quadratic terms. So the thing is that if I take the order, let's say instead of 2, I take 3, you will also see that you can come up with a factor z transpose z. So this is basically the example of this polynomial kernel. There are some other examples of this polynomial kernel, like linear kernel is simply the dot product of whatever we have seen in the original space. We have this polynomial kernel of order of p, that in the yellow p can be equal to 2, 3, 4, 5, 5, 6, and so on. You can have some Gaussian kernel or the RBF kernel, which basically compute the Gaussian similarity, and we can have the sigmoid kernel, okay, which basically computes the 10 hyperbolic function of the dot product, that is x transpose x. Is this clear? Is this clear? Yes or no? Why nobody is saying anything? Can you? Am I audible?
Yes, sir. You are hearing me, sir. But actually, it's not very clear. That's why it's silent.
Okay, this thing was very simple. Where did we start with? If I move to the z space, remember, if I move to the z space, I have to compute z transpose z, right? So there are different j's. It's a different z. That's why I have to write z. If I write from the point of x, how will it look like? It will look like phi of zi transpose phi of z of j. Okay? Oh, sorry, my mistake. What did I write? Z over j. X. Now, if I look from the point of x, are they linear? Yes or no? Look from the point of x, are they linear? Of course not, because we have this phi function, right? But if I look from the point of x, are they linear? Yes. Oh, sorry, if I look from the point of z, they are purely linear. So that's why what we have said over here, if I go to this particular figure over here. So if you look like this, from the point of z, what we have computed? We have to compute z transpose z, which is linear. That's why here you will see that this is a decision boundary, and this one is a linear one. But if you look at the same decision boundary in the x space, the decision boundary will look like this. So is it linear?
No, sir.
No. And why was it non-linear? Because in the x space, you had to compute phi of x, then you took the transpose of it, phi of x. And the definition of the phi function, the definition of this phi function had to be something like, maybe something like this. So if you look at the definition of the phi, is it linear or we have the quadratic terms over there? We have quadratic terms over there. That means it's going to be non-linear. So if you compute this phi transpose phi, that this is basically phi transpose phi, and if I do some simple calculation, this ended up with something like this. Yes or no? Right?
Yes, sir.
Okay. Now, if you look at, instead of looking here, instead of looking there, which is very expensive to do this calculation, I have to compute x1 square, I have to take x1 into x2, then x2 square, root 2 of x1, root 2 of x2, and blah, blah, so on. But if I look at the simplified version, but if you look from the bottom to top scenario, this value is same as the one that I have marked over here. Okay, that means this is the same that is computing this. So if I compute this, is it expensive to compute?
No, sir.
Why not? Because we simply have to compute a simple dot product between x transpose x, but we have to add 1 and then take the square. So the computation is simple, but it is giving the same value as computing phi transpose phi, right?
Yes.
So that means, I mean, this is equivalent. Remember, this is equivalent. No, you have to remember, like, this is equivalent. Okay, that means computing this one is expensive. If I write it, this is expensive. But computing this is much simpler. So which one will you pick? Something that costs the same, okay, but sorry, I told the other way. Something that gives you the same value, but it costs less. Which one will you take?
That one, the one that costs less.
Yeah. So basically, you're having the same output. Remember this one. Same equivalent output. It's the same output, but you can do it. You can get this output by the one which is much simpler. And this computation you have done in which space? In X space or in Z space? Remember, Z space computation is X space.
Yes.
So where do we go then? We do the same calculation in the X space. That's why you see that all this kernel calculation. Are we doing in the Z space or are we doing the calculation in the X space?
The X space.
X space. But the output is equivalent. Remember, the output is same. I will not say equivalent, is same. Same in phi transpose X, phi of X. So if I just want to differentiate, I will like X sine Xj. Or this is same as equivalent as Z transpose Z. Is this clear?
Yes.
Yes, sir.
So that means with a kernel trick, I can save computation, but I can get the same output.
Yes.
Okay. I think we can stop up to this.
Yes, yeah.
Okay. So I just give you the link to your attendance. Your final exam will be starting from lecture 8 to lecture 15. So today's lecture is lecture 15. So you will have several questions and all the questions will be mandatory. So you won't have the options to choose from. Is it okay for you?
Yes, sir.
Okay. So I think we just have to conclude this course actually. So though I wanted to cover at least two other topics. One was collaborative filtering, that is a recommender system, and then I want to cover reinforcement learning. So due to the shortage of time, and I couldn't increase the pace of this course actually much. So I just lagged two topics. So I will post an assignment today. That means I've said that you have to give a summary of this course, and also you have to include feedback and criticism of this course taught by me, and you have to upload it as an assignment. Sorry, as a quiz. And I will give you the deadline until 30th of January. Is it okay?
Yes.
So I will give you until the 30th of January.
Sir, for the exam, could you make question is optional?
Sorry, can you repeat that again? I couldn't understand.
For final exam questions, could you make them like optional, not mandatory?
Okay, I will think about that one. Okay, but I cannot assure you right now.
Okay, sir. Thank you.
Sir.
Yes.
Welcome, sir. Sir, regarding the syllabus, can we exclude lecture 15 especially, because I feel like it's probably, I don't know if it's a personal thing, but I feel like I'm not really following too much on lecture 15, and I feel like it could be if it's excluded, then I can focus on 8 to 14 better.
No, sir, I think it's the Lagrangian multiplication it wasn't actually covered in our math topic, so it's a bit unclear.
Okay, you don't have to worry about this Lagrange multiplier, because in my lecture slide you won't find much about Lagrange multiplier. I just mentioned about Lagrange multiplier, that why it is used for constraint optimization problem. I just mentioned it to just make you clear that this can be used in case of this problem formulation of S1. Do you understand?
Sir, actually now we will get only 1 day before exam, and since
Yes.
there is only 75 marks, can you please omit the last lecture actually?
Okay. The thing is that your exam is on the 21st of January probably, right?
Yes, sir.
And do you think all the questions will come from this particular slide?
Sir, but if there's no options, we will not get any chance to It's Friday.
Okay, so I will think of giving an option, okay, but I have to include SVM because we don't have many topics that we have covered. So what did we cover? From lecture 8, we started with neural network. We went towards deep neural network, convolution neural network. We had some examples, architectures, and then we moved on to confusion matrix, and then we moved towards unsupervised learning. That means PCA. Then we have clustering that K-means and K-medoids, and then finally we ended up with SVM. So the syllabus is very small actually.
Covered classes on Bayesian classifier.
Sorry, which one? Oh yes. Yeah. We have. Oh yes, we have name-based classifier, and then we have decision tree, right? Yes.
So there are actually quite a lot of topics.
Lot of topics, but I missed a lot of other topics that I could not teach in this course, like collaborative filtering, and there's another one that is known as outlier analysis, and then finally reinforcement learning. So 3 major topics I could not cover. I think it won't be much of a problem. I believe so. So don't worry.
Sir, then at least, then can you please say before, can you please include an option like 3 out of 4?
Okay, I will try to do that. Please, I haven't said the question yet. I will think of that one. Don't worry.
Thank you, sir.
Thank you, sir.
So, okay, so this is it. So we have reached to our end of the course. So though our objective was to make a machine intelligent, to make it learn and to make it take decisions. So whether the robot that I showed at the very beginning, to make it learn and to take decisions. So how intelligent it is after this end of this course will depend on how good you do in your exam, right? Yes or no?
Sure.
Okay, so I believe you will do good, right?
Inshallah, sir.
Inshallah,
Sir, can you please give us, sir, some suggestions on what to focus on, how to prepare for the final? I mean,
I will
anything
try to do
like
that. I will try to post that in the Google Classroom.
Thank you, sir.
Any further questions?
Sir, in
Sir,
the final,
regarding the go ahead.
in the final, will there be questions that you gave us on the mid for 15 marks and 17 marks?
Yes. The questions, the numbers can vary significantly. Something, the broad questions will have more marks, the short questions will have less marks. The question pattern will be similar to whatever I have given in the midterm exam.
Okay, sir.
Sir, another request. So in the mid, there was a 17 marks question in one question. So is it possible to decentralize those questions a bit? Because if someone can't answer them, then 17 marks is a huge
Okay.
pressure on.
That means you have comparatively shorter questions so that you can have more options to answer, right?
Yes, sir. Like lesser marks distribution. Like 17 marks on one question decreases our chance to get more to get marks. Okay.
Okay. I will keep
that.
Okay, I will keep that in my mind actually.
Sir, also about the midterm exam results is like.
Okay, so I couldn't, it is basically finish looking all the scripts, so that's why I couldn't publish the results actually.
Okay.
Okay, Sim, is the Juma prayer is very close, so can we end over here?
Yes, sir. My prayer is now.
Okay, thank you very much. I've given the link to your attendance. Wish you all the best.